Okay, so my laptop's recording the content, and we should be all set. All right, let's talk about. So let's talk about this, and then that'll make the articles make a little bit more sense. So here's the lecture that I want to talk about. Okay, so there's obviously a fair bit of math required that's involved in actually calculating these points. And we're not going to go into the math, but we're going to understand how the math works. And we can understand how the math works with just a basic understanding of trigonometry and geometry that you probably picked up in at least college algebra, maybe even high school geometry. Okay? So if you think about the definition of what a point is in space, it says here, what do you guys see now? Yeah, you see the same view. Okay, I'm just going to leave it like this because it's bigger. The location of any point in an image can be described with just two coordinates, so x, y. Sometimes in image science, we refer to that as just the image coordinate. What we really want is the location of a point in the real world described by three coordinates, x, y, and z, a latitude, a longitude, and an altitude. Okay? So the real world's three-dimensional. So we want to be able to go from having a bunch of pictures to creating a three-dimensional rendering. Okay? So yeah, it takes there's like a little tool that you can use to tighten that up, but I don't have it right now. Should be a little bit better. Okay, so we're gonna talk about this data processing pipeline, and a lot of the terminology that I'm going to use is it's cross-platform. In other words, it doesn't really matter which software package you're using, although some of it applies specifically to Pix4D, but most of it does not. So things like calibration, point densification, orthomosaic. Those are all terms that almost all of these software packages use. So the first step in this process is basically to take all of the images that have been collected looking at a specific location and figure out where the cameras were during that process. That's the point that's the step that's called calibration. And once that's performed, we can infer the position of lots of other points. So we're going to talk about that process, the processing pipeline. We're going to talk about that. We're also going to talk about accuracy and what affects accuracy and what affects processing time. These can take a little while. So this is one of the basic principles of photogrammetry. So we've got our camera. This is like a model of the camera right here. So on our camera, what's happening is that for every pixel in the camera, there's a specific ray that's associated with what gets turned a specific color or gets recorded as a specific digital number on the image sensor. So this ray is coming from this angle, and actually it reverses itself. So the elements that images over here get focused onto this side of the image sensor. But just because it's a ray is like can be given by an angle. There's an angle out from every pixel. And so whatever it is encountering could exist anywhere along that ray. Does that make sense? Like, for every pixel, there's only a given set of locations where that pixel could exist, and they are all on that array. That ray, sorry, not array. So for this pixel, the possible locations for that particular pixel, the object that was recorded by that pixel, can only exist along this track. Okay? Now, to really know where those were, we have to know where the camera was, and not only do we have to know where the camera was, but we have to know the angle of the camera in order to actually come up with an absolute location. An absolute location meaning a latitude and a longitude and a z value. But just knowing the camera parameters, we can infer that the thing that is being sensed is somewhere along this line. Okay? So the basic principle here is that if we have two cameras and we see some entity and we assume that that entity didn't move, only the cameras moved, in our case the cameras moved, or it was two cameras, then we can know the position of that particular entity because it is the intersection of those two lines. So we can find out what that 3D location was because we know the location of this camera, and we know the location of this camera, and we know the focal properties of this lens, so that we know what this ray, the direction of this ray, is taking away from the camera. And so any object that we see occurs at the intersection of those two lines, and using the angles and the distances, we can infer the 3D location. So that's the math that's occurring behind the scenes for photogrammetry. So really, in order to get this location, we need to know the location of each camera's center. I took this from British Slides, obviously. Okay, the orientation or rotation of each camera about its perspective sensor. And we refer to these two things as the exterior orientation. And then finally, the location of the point on each image sensor. Because every pixel is pointed at a different ray. Okay? There's a different ray for every pixel. But the software takes care of calculating the ray for every single pixel based on a knowledge of the lens and the focal length and the number of pixels. You know, the size and the number of the pixels. So here's an example of two different pictures. And so the first thing that the software does is actually, it goes through every single picture. It starts with the first picture, and it uses image processing techniques that you're probably all familiar with if you've taken remote sensing class, and if you haven't, it's no big deal. But it looks for edges. It looks for unique items, and it stores the pixel values around those unique items. And it stores the location that they're in the image, and it stores what they look like. It stores all that data. So for every single image, if you have 600 images, it goes through every image and tries to find unique spots. Okay? Then, the second time through, it takes all of these unique things that it found, all these unique pieces of your image, and it tries to match them. By the way, it calls those unique things key points. So it might find 20 key points in an image, it might find 100 key points in an image. What do you think is the main determining factor as to how many key points it finds in an image? And we're not even talking yet about stereoscopy. We're talking about, this is actually the first step, and it's more of an image processing step. And in the image processing step, it's mainly concerned with things that it thinks that it can, not things, but it's trying to find things that are unique in the image that it will be able to match later. Yeah, so it looks for color differences, it looks for contrast, it looks for sharp lines. And it's one reason why this process works a lot better in a built environment, because there are lots of sharp lines that are easy to find and to pick out. If you think about looking at a forest, right? If you've looked at aerial photography before, or even a green grassy area, there aren't a whole lot of unique elements to pick out of that area. And so it won't find as many key points. And when we run our data, the report is actually going to tell us how many key points it found in every single image. So you'll be able to see that in areas that have more sharp details, things that they could pull out as edges and unique features in image processing routines, those will have more key points. All right, so once it creates key points, it tries to match those key points. In other words, it says, this key point looks like this key point. So I'm going to at least say they're the same key point. Right? So that's what happened here. This key point and that key point were judged by the software to be the same key point. And so it found those two key points, and then using the camera model, the focal length, the principal point, the lens distortion. So all this stuff needs to be known by the software for this to work. It needs to know, like I said, the focal length. The principal point helps it to compute all those angles. The principal point is the center. It's the pixel that's pointing straight out from the camera. And so with the lens distortion information, it can infer all of the rays for the rest of the sensor. So the principal point is which pixel defines the center, where the ray is pointing straight out. And then finally, you need to specify the lens distortion. Now, most software that's out there has a number of cameras stored in its database. So you don't have to actually know that. And really, all it needs to do to infer all this is to know a few key specs about your camera, which you can often get from the manufacturer. Now, a long time before lots of people were doing photogrammetry was still used a lot. It's actually used to create, all the digital orthophoto quads. Okay? The DEMs, where the contour lines are drawn in on those were derived from aerial-based photogrammetry. It wasn't digital photogrammetry all the time. Sometimes it was actually human calculating these numbers manually, but it was calculated in the same general sense. And in that time, they were using cameras where they were referred to as metric cameras. Metric cameras, meaning that all of the information about the camera was known and was certified to be of a certain specification, and they published it along with the user's manual and everything you needed to use the camera. And so it had a very high tolerance as to what was accurate, a metric camera. So you may hear that term. And in fact, when people started using drones for photogrammetry, sometimes in the literature you'll read studies using non-metric cameras to calculate, to infer positions using photogrammetry. So, anyway, that's the difference between you might hear that term, non-metric camera versus a metric camera. A metric camera is a camera that's been designed for photogrammetry, and it has very specific measurements that are published. But even if the camera is not metric, like the ones we used for this class, the basic information about the focal length, the principal point, and the lens distortion can be found by the manufacturer. And even if you don't enter it exactly right, as long as you get some ground control points, you can still get some pretty accurate information. We'll talk about that in a little bit. But this is the reason that the focal length is so important, because the lens is what focuses it onto the focal plane here and creates the image. So we kind of talked about this a little bit the first day, or maybe it was the second day, where you get further away, and obviously you'll have a wider image, but you'll have less. You'll have larger pixels. Now, in this case, remember that a longer focal length is like saying it's more zoomed in. So a longer focal length means that you have less area to image. So given the same area to be imaged, you would have to fly higher with a longer focal length camera than you would with a shorter focal length. All right, now, we obviously took a bunch of pictures. The reason that we took a bunch of pictures and we have lots of overlap is that the more of these key points that can be turned into matches, it will increase our accuracy. So here we have a slide talking about the relationship between accuracy and the image. So look, if we have two images and we infer that this particular ray is going in this direction, but in reality it could have been anywhere from here to here, same with this one, then we have an ellipse that forms the error. In other words, the three-dimensional point could be anywhere within that ellipse. So the more points that we have for that particular area, the better. And also, one thing that's harder to visualize here, but we'll show it on the next slide, is that the further away those 2 points are from each other, the smaller that error ellipse gets. And so this is actually one reason why flying higher will, all else being equal, the higher you fly, at 70% overlap, you're going to get further away than you would if you were flying lower, and even at 70% overlap, your next picture isn't going to be as far away as it was previously. And so your error ellipse is going to be smaller. So it might seem counterintuitive, okay? But the further away from the object you can get, in one way, the smaller your error ellipse gets. But what's a way that it actually gets bigger? Can you think about that? Like, the further away I get, what happens to my spatial resolution? Your pixels get bigger, and if your pixels get bigger, and we're relying on matching sets of pixels that look similar, right? And we're inferring a point from those pixels, then the fuzziness of where that point is also gets bigger. So as you fly higher, the the error ellipse in terms of where that might be in three-dimensional space gets smaller, but your precision, I guess is probably a better way to say that, your precision gets bigger, which has the same effect as making the error ellipse larger. But there's two different processing steps that are going to go on here. The first step is that we have to be able to find key points, right? The software has to be able to find key points. If it can't find key points, then it can't even begin to infer where the cameras are. Okay? And so the spacing of how far out they are is important to that process. So sometimes when we fly higher, or we kind of fuzzy up our data. In other words, we make the sampling size greater. Anyway, we'll talk about that in a second, but it's really important to get the key point model built. And so for right now, let's just focus on you want to be as far away as possible when you collect your next image. Now, I guess that's not actually the right way to say it, right? So if you take an image here, and you take an image here, and you take an image here, and you take an image here, that's great. Much overlap as possible is great. But what you do get from flying higher is that you're going to get further along this way and still be taking an image back to this original image. So it doesn't, it's probably better to have 1, 2, 3, 4, 5, 6 images that all overlap than just taking one here and one here. Okay? But the important thing is that you have that image that's way further away. Okay? The distance between those 2 points. I mean, it's actually the exact same thing. If I'm going to stand here, and if I wasn't exactly sure whether somebody was in front of or behind an object, if I move a little bit, I might not be able to tell, especially if they're really far away. Right? If I move a little bit, but if I walked, all the way over to the other side of the room, I could start to see the relative change in their position. In the position of 2 cars that are way out in that parking lot, I can say, oh, well, I know they don't change all there. Which one's in front of which one? But if I move way over there, I can start to see them move relative to each other. And yesterday, but we went to Tallahassee to visit my sister-in-law's family at the end of spring break. And I was driving back, and I saw something way out in the water, and I was wondering, see the Gulfport skyline, but then I realized it was moving way too fast to be that, and it was just some other building that was out at the end of the current ocean that we were passing on the other side of Mobile. All right, so that's the reason that it's important that we have images as far away from each other. So if you ever try to collect data and you run it through Pix4D like we're going to do today, and it just doesn't work, it says we couldn't find a solution. We couldn't find out where these cameras were. The solution is usually to fly higher. And then I'm going to talk about the second one. I tried to bring it up already, but I'll talk about the second one later, and that's to take your data and resample it. On Pix4D, will do that for you, but if you were using a software package that didn't, you could do it yourself. Okay, so photogrammetry. This actually says structure for motion because, but it's photogrammetry or structure for motion. The surface has to be textured, so image matching doesn't work on featureless surfaces. So, although natural surfaces are usually sufficiently textured, it can pick out little differences. If you have the spatial resolution to see, a particular branch on a pine tree, it'll see that particular branch on a pine tree. It could also see pattern patterns projected. Another thing that you can do is you can lay out targets. Whether or not, we're going to talk about ground control, because we need to, because for next week we're going to do, not next week, but the next time we meet, we're going to do ground control targets. But you could lay out targets even if you don't collect ground control. So let's say we were doing an area that we knew had very little naturally occurring undulations or changes, texture that we could see. You could lay out some ground control targets. And ideally, you would want to have the ground control target visible in at least 3, but usually many more images. That's your goal. So you must be able to see every point of interest from 2 locations. The shadowing effect is twice as bad as the laser scanner, so you need to take images from different vantage points to fill in the shadows. Shadows are really difficult for images to work with. In fact, if you're acquiring data, we already talked about how shadows were kind of bad in terms of the imagery just not looking right. They'll have lights and darks. It also really affects the ability for the photogrammetry software to see matches if the shadows are changing, like they're taking too long to collect your data, or if they're coming in and out. So your subject should look similar in each image. You don't want to have a lot of shadows in your images. Don't collect them at 2 different times of the day. We have actually had times, I think I showed it in this class, where we had a really big mission, and we collected it all in about an hour one day, and then in about an hour the same time the other day. This was taken over 2 days, and it worked out well. Actually, all of this data right here was over 1 day. You can kind of see that there's a little darkness change the next day, but it worked out better than I thought it would to collect over a 2-day period because both days were bright and sunny. This was a little bit later in the afternoon. Okay, now what I'm talking about in terms of having big differences in color are okay. It is interesting, if you're trying to take pictures and you have small moving objects, they won't really be a problem. In fact, you may not even see them. In things like swaying trees, also, sometimes swaying trees are just left out of the equation. So if you're actually trying to collect tree data, sometimes that can be a problem. But I do have an example of that. That was in the. We'll zoom into the Cayman data that I showed you on the first day. There were lots of swaying trees. Okay, so you can see this data here. And what's interesting is this was a really windy day. I'm trying to do this. The orthomosaic off. But see particularly these like wispy trees right here. See this is a really wispy tree. Turn off the ortho. And some of the tree got captured, but part of the tree, this whole part of the tree right here, didn't get captured because it's a wispy tree and it's really blowing in the wind. See how this tree also, some of it got captured, some of it didn't. I don't know what the name of these trees are, but they're kind of really wispy trees and they're moving back and forth. And even in the ortho mosaic, you kind of see how it gets blurred because it's 2 or 3 separate images that's calculated, that are calculated. But it doesn't get built in to the DEM as well as some of these other trees right here. They're kind of compact canopies, and so they're not moving as much, and they build a better DSM than the areas around here. Those wispy trees. I should find the scientific term. Larger swaying trees can be an issue in creating an acceptable model if it's a really windy day. All right, this is what we're going for. This is an uncorrected vertical aerial photograph. You see this line, yeah, that line might not be straight in real life, okay? But it actually is straight. So this is a cut through the woods for an electrical line. So our goal is to create these ortho photos from the uncorrected aerial photograph. So what happens is once all of the key points are found, then the cameras are calibrated. There is a number of points, and it actually usually ranges in the thousands, sometimes tens of thousands. It's a lot of points, okay? But it's not enough to create an ortho photograph yet. It does create what's called a preliminary orthophoto, okay? But it's not as high detail as what you actually want. So that's step one, and then it takes all of the locations and it starts trying to find other matches. In other words, kind of like more key points based on the key points that already exist. So it finds more areas where they match up, and it densifies those points. So it creates additional points, and then it goes through and it actually finds cases. It says, okay, well, I found a bunch of points that match up really well, but there's some points that if I include these points, the data is going to look really weird. It's going to be impossible for it to happen. Okay. So that's where it filters out some points. And then finally, it generates these products, the digital surface model and the orthomosaic, by projecting the points onto a flat plane. All right, so this is where I want to get into actually doing this process, and we'll go through some of these slides later. But I'm going to open up Pix4D. Did I post the username and password yet? I didn't. I'm going to do that right now. So right now I don't have this installed. Like I said, we can only do one at a time. But you can go ahead and do it online. The disadvantage of doing it online is that you cannot change any of the default parameters. So if you have an area that's hard to stitch, it won't work as well. But it's a good starting point. So that's not where I meant to go. USM, instructor, courses. I really thought that I posted it. Okay, so I actually have to log out of this machine because I was planning to use this machine. So hold on just a second. Pix4D mapper. Okay. So I actually usually have 2 licenses, but PhD student seems to be always logged in. He's down in Ecuador. So there are 2 licenses. So sometimes if you see, I'll tell him to log out when he's not using it. We'll see what happens. Okay, so the username is my email here, my USM email. So that's george.raber@usm.edu. And the password is the password that I use for lots of department stuff. But it's not my password to check for the administrator password on this machine. So it's about the most secure thing you'll get. So I'm going to post this as pics 4D. I'll just post info. Is pretty sure it's capital GEOG 5051. On to the local versions when I install it. So see how right now it says 1 of 2 available licenses. I can see I'll be able to log in. So yeah, so Chris Hare down in on it. He's been logged in since January 28th, so I should ask him if he can log out. So anyway, 2 licenses available. If you see 0, you can actually start your project. You can set it up and set it later, because it'll still let you into the free version. So you could say OK, and it'll run in discovery. So it is capital G. So I'm going to go ahead and save this announcement. So now it's all right. So this is what you see when you open Mapper. Just want to make sure this. On my screen, it's slightly cut off. That's why I was making sure. Okay, so this is going to load some of the data that we collected last week on here as an example. I have it on my laptop, but I haven't. All right, so here's one of the missions that was 375 feet. I have all the in onto the cloud, but it wasn't uploading from my house. Put it up there. Put this on. Hopefully I can write to this C10. Okay, so let's start our project up first. Actually, while that's copying, I want to talk about the images. Here's the images that we collected. Mission this was a photograph. These images actually look, you know what I mean by that? Like they're a little darker than they should be. And I think, yeah, they look pretty dark. I think that's because that actually looks pretty good. Exposed pretty well. But anyway, these images are a little bad. It's way better to be underexposed than overexposed. A bit on the underexposed side, just say, oh, I'm lucky. If you're overexposed, it's really hard to get any detail out of pixels that are at the. It's a little easier to lighten up pixels. Obviously not going to work, but if you have pixels that are just too dark, enough dynamic range, images themselves to brighten things up a bit. So you you can see how there's this like there's also this little shape here that the software is going to be able to recognize. See, when I move forward, I can see that same thing again. Move forward to the next one. That object, that particular object. I'd be surprised if that's one of the key points, and we'll be able to see that as it things like these to be able to look for, but it's looking for. So when I point out that thing, like this guy right here, well, I can use a different one. But yeah, when I say find just like a piece of it or another piece of it, another piece of it, but several of those unique, and it's going to use those to calculate the camera position. So. 339 images in this one. And it did get kind of dark here at the end. It'll be interesting. So you can see some examples of things. When you first start up Pix4D Mapper Desk, and concurrently with this, I'm going to just show you. I'm going to show you how you do this on the web. So you just hit New Project here. Then you upload your. I'm going to get rid of that. Number one is a terrestrial photograph, and it's not part of the model. And then just drop it in them all. All right. Just hit process. That's the only option you have on the internet. Okay? So you have to come up with a name. So I'm going to call this GHY Phantom 375. And then this is all right. So next I need to add images. On the allow you to add any images that have the same name sometimes, right? Because if you on most these cameras, but most cameras, it actually starts reading. Have you noticed that? Okay. So if you tried to do that on the internet, so I wrote a little Python script that contains all the files in a directory, and you solve the problem. Here, it doesn't care. Or alternatively, if you can just hit add directory. You'll notice that there's a button here that says add video. You could actually have been recording video as you went. Still, you can give it an interval, like every half second. The quality of that. If you think it would be higher or lower, then yeah, it's lower. It's much lower. A video camera even is less than either of the two cameras we use. 12 megapixels based on pixels. Then to consider, we talked a little bit about rolling shutter versus a global shutter. On the Mavic, it wouldn't make much difference because it's a rolling shutter in both cases. But it's in video mode, it's still using a rolling shutter, scanning to take the video. In mode, it's taking pictures as using images. I'll have more distortion. So I've seen people use video in certain. But if you have a stills, and those stills are much better, don't use the video. It's going to end up using stills anyway. I'm going to add my images. I put them right. That's the directory I just created. So I put them in this PC. 375. ArcMap and ArcGIS Pro is in. So the project, it's going to always look for the images. It is kind of convenient if you open it, where are they? And if you specify that they're in a different location, sync up with that different location. But there's no way to, like in ArcGIS, you can say, you can't do that it will ask you where did they go. So sometimes I didn't do them in the same location on disk, so I can just do it. But I have them stored in two different. Now the products that it creates will all be, and sometimes that's all you care about is the products. The points, the matches and their locations, the cameras, and the actual products, and the dense point cloud, and I guess the mesh as well. All right. Okay, so it's reading the EXIF data. I don't know what it is, but it's the camera, all of the metadata. It now knows camera. This is the camera. So it knows that people want to use for collecting data. The code for a phantom. In fact, if we open up in here properties, then you can see that if you go under detail. So under the camera, the 6310, that's this information here. The 8.8, notice that that it just kind of rounded it, but they know that it's 8.8 millimeters, and it actually that's the. If we go over here to edit. I'm not going to edit this because GHY told them all this information. If we did have a camera, we would change it right here. And so, like I said, you can manufacture the exact image height, get that information. The focal length, kind of a little bit counterintuitive, but it will have focal length. It will calculate this back over to that field. One or the other. You don't have to know both of them. Millimeters, that actually says 8.6 instead of 8.8. This is the accurate number. Yeah, the sensor height. That way you can calculate all those rays. And this would definitely probably find online for any camera. There's a company that makes the sensors themselves, and so there's lots of camera sensors. Information, maybe you have to send an email out there. Plus, softwares now have almost every camera you can imagine that you've ever wanted. This is with that really harder to find online, but you can actually calculate your data without that information in as part of the processing step. It will infer that information, and then you can save that out. Like you can save out your after it's done too. You can create a new camera model as long as you get pretty. Also, this is later when we start. Remember, I have that phantom that I modified the RGB, so we can get the bands here and specify a different set of bands. So we're going to do that. Camera that you've modified yourself, you've had somebody modify. wavelength right here. And the reason that the reason that you would do that in cases where one band contains just can enable it, or band is going to be, there's going to be more contrast in a particular band, you can weight that out. For example, the default configuration weight placed on the blue band. Scattering associated with it. They would use these particular parameters, but this camera, that those are the parameters to use, is weighted the highest. These are probably tuned for green as a big contrast between vegetated. So you might want to weight your near infrared band pretty high in areas where you had one of those. We'll process that. Talk about that a little bit more when we process that other data. Now, these other things are important. It assigns the all of the images that you put into this. A group is a series of images that you know all overlap. So you can't, you know there's a gap between two areas. Or you know that there is some overlap, but you know that there's not going to be a good match in that overlap. Those pictures to one group that are in another group in another area, and it won't try to. Then, once it's all processed, you can that would cause those two groups. Two different groups here. Where's that from? That from the GPS. It's in the GHY app. When it says it's down here. I'm clicking on multiple images here. So it said multiple. I just click on. I go down here, and you can see here's the longitude, and there's the altitude. The altitude is often the most, but it seems like in Phantom 2 there's like some doubt, and that's reflected in default values it gives for and vertical accuracy. Accuracy by default is 5 meters. An off-the-shelf GPS that you get for that's probably the cost of the GPS of the. It's not a high accuracy GPS. I said before is the realistic accuracy device, and then the vertical accuracy is altitude here is 95 meters, and we knew we flew. For me, it was 370. I forgot exactly what it was, but 95 meters. So we got 311. It's off. This was not the mission I thought, and somebody did fly this at like 320. All right, and if you change these numbers, what it actually says is that, and if I see two key points and they match up, there's no way they're within 5 meters. So if you you're going to get more key point matches that may or may not. So if you make these numbers, okay, well those really could be 2 key points, and it may connect two. There might be a similar class somewhere. It might try to connect make your model distorted because of that. That it does. It also says, is it possible that object, it's not possible. There's other checks that it does. Also, increase your processing time. You're going to check all of the points for possible key matches, and it is possible to actually throw out values and not specify an accuracy. It increases your processing time. So I've included, which is an article that we submitted this week, one of the readings I submitted. This is an article that we submitted. Because we were working underwater, we didn't have a good way to control, and so just everything after results is interesting to your application here. Got how it took 3 or 4 days sometimes to process. So it is good to have that accuracy because it make these numbers, the faster processing time, also the better result. Okay, it will always choose by default. To use the proper UTM. If you do not have data, it'll choose. That's where it'll just it'll pick one of the cameras. That camera is 0, 0, and everything else is going to be relative to that camera. Oh, and use a specific coordinate system for your output. You can you take this and you can import a PRJ file. You could select if you wanted to do Mississippi Transverse Mercator, it might not. If we had a PRJ file, that's just all of the some spatial group is the somehow everybody's adopted using for specify to use, and we can also specify to use. I'm just going to accept the defaults there for now and use the so that's the coordinate system that we're going to use. All right. Okay. Just a set of canned parameters. So right now, we're using a few more, and you're choosing what outputs you want. One of these, like let's say I want to choose, that's probably the one we're going to choose most often. It's going to select the output to choose. It's going to choose 3D mesh. It's going to create a 3D mesh and a point cloud. Basically everything. It doesn't attempt to output a orthomosaic. So I'm going to choose 3D maps. I'm going to show you is this output you what it's choosing there. I'm going to go to model. I go like this. See how it says the output's quality. Why does it get low? Processing speed go up. That's what we're going to talk about here for a few more minutes before we run it. If you go to online, that here is our processing. It says it's going to take 2 hours and 15 minutes. So it started processing that. It just went right into processing. It's by the way, it's choosing. That's what it's doing. So it's on the quality reliability, but it's on the slowest processing speed, and it's out. Two things added: the ability to kind of choose these defaults. Under maybe they. I thought I read. Maybe that was I'm not sure. But I thought they were adding the ability to change the template. So I'm just going to hit finish now. The first thing that comes up, if you had dots, had cameras that had GPS locations, this is okay. So collected all these points. Now, one thing that's interesting is oftentimes don't show up quite the way they show up. It looks like you think they should all be equally spaced, but they never actually end up equally spaced. There's out there that are very good at equally spaced, but the Phantom cameras are like this, where sometimes there's small spaces. But that's one reason why on the side of selecting more. So those are you can click on any of these locations and start to get the information. That's the picture. So on. I'm going to go processing options. These are the defaults. Okay, that's on here. It says key point image scale. We're using Pix4D here. Standard, the photo scan has if the ArcGIS implementation has this or not. We will look into that this semester. But that is the parameter that I was kind of trying to talk about before. I'm going to look at every image to find my key points. First step it does is it goes through every image and tries to see other images. Full, what it does is if you choose, you're able to resample the image. It basically before, and you choose to do image size. And what it's going to do is take the image. So what that means is that you have 2 by 2 centimeters instead of 1 by 1. Quarter image size to be 4 by 4, so that's 4 by 4 centimeters. That's only the thing that's going to use to calculate key points. Is that when it creates those key points, it's going to match larger pixels. So the precision point gets lowered. The advantage, though, is that are actually easier to see in simpler, and oftentimes it actually it actually finds a few more key points. If I'm looking for things that are like 1 centimeter big, I may for little leaves on a tree, whereas if I sample this 7 centimeters big, now I'm a branch, a pattern on a branch, and so that's better. Okay? But the is now a little bit more fuzzy, and so if you initial key points may be less accurate, but actually I might get oftentimes to match well. So sometimes if I run it through initially and it doesn't work well, a different value. I'm actually for size faster, and then let's go to map. Default. This is the default where you have GPS, and that makes the most sense for us. So, what this screen is really about, and it tries to match them up and say same object as this one. If it can weed out images that it knows don't overlap faster, because it doesn't have to compare all of the key points in this, all the key points it found in the images way down here. So it doesn't have to be any key points in that image that are on this. It only checks the image that is of overlapping based on the accuracy data that you gave it before. Okay. That's actually what makes it go faster, is choosing that. Any GPS information, you should not choose that. Also, if you choose food fighter terrestrial, it'll still use the GPS. It won't also use the flight pattern as anything significant. Information, you can choose custom. Custom is what we had to do in our reconstructions, and if you any other thing where you didn't have GPS information, and you can actually select distance if you want, but GPS for that. So capture time is good if your camera has, which is what we did on the coral reef, because you can say, okay, well, definitely images are more likely to they're collected around the same time. You can specify how many images typically overlap. Also, you can use image similarity. In other words, look very similar, then more likely to actually contain some overlap. So you can use and then choose to select manual tie points. Talk about that once this is processed. And then you can specify if you also have cameras. In other words, if you have data with two different physical cameras, if you check that, then it's expecting even camera at the same time for the same. So you want to make sure that's unchecked. You're collecting data with two cameras, and you are both. So that's all those. Let's change this back to aerial photos. That's what we did. And that's what you'll do most of the time. This is mostly for you would go in and kind of change these. This will increase your processing. Okay, so use geometrically verified matching. I would recommend you not checking this. It sounds like that's kind of good, and it is. It'll increase processing time because it's going to find out if the matches that you got, are possible. In an aerial grid pattern, it's very unlikely ones that would need processing time unnecessarily. However, if you did choose custom, information, I would check that. Also, sure about your camera model. If you're using an extra that you entered yourself, because we're not going to change any of that. I only change. And then under what it's going to do is, if you go through and use its own to it's going to find more key points in some images. It'll if it finds this many key points, it won't keep trying to find more. So you can increase processing time, but again, you're sacrificing a little bit of when you tell it to just find a certain number of key points. The defaults here are automatic. I like to keep that. I like to keep that the default most of the time. So it will, once it actually calculates the position, it will calculate a new camera model different than the one that you created, particularly not entered all the distortion parameters. Leave that checked if you want to have a new camera model file. That's where you check you have any sky in these images, it usually screws it up. But you can bebop drones, I guess. Bebop actually is a fisheye lens, and so it has a lot. Okay. Anything else I want to start this process up, and we'll see it work through. Oh, there was back here. So it's going right now. I'll come back and talk about that. So now it says it's doing it pretty fast. Think about it. It's calculating thousands and thousands of through each one of those. That's in real time. It's pretty quick. It can find. So it's just running an image processing routine in each one of those images. But while it's doing that, it's doing that at half image scale, so it's fast the full image scale. I checked this generate Oracle Mosaic preview. But that's another option that I always like to make sure I have. Now, in reality, if I wanted to, another thing, if I wanted to do this camera internals and I actually wanted to make that, I should do this at full scale. The results of this output to really replace any camera model that I already had, based off of a camera that basically camera that actually was used. For our purposes, it'll make this step to do that. But that's lying further apart. The other way to make your error band bigger by choosing to use 1.5. You're making your error band bigger because you're saying that the point exists, making that circle larger, which has concerns, but see where that. Okay, so once it finishes this, and then we'll take. I'll make sure that it's not going up. So the next the key points is it's going to go image by image, and you'll see kind of turning blue. And what it's looking at the surrounding image, light up blue. What it's doing is saying, okay, I found a match in those two. You'll see that it's only considering the images around, or it's using the. See how it's the third one. Now it's on the fourth one, and the other ones that are finding for that one. So find. Whoa! See how it like lit up way over? Get thrown out eventually. It's probably over the water and maybe similar things, but. Hasn't gone through the step of actually that match could really exist. Just finding, so if you can imagine a table of all the key points, it's establishing relationships between the key points in the database. So the next thing that it's going to do is it's going to go image by image. I'll let you go for this part, but it's going to go image by image. All of this images, and it's going to use all those camera. In other words, infer the position of all the cameras, and then it's going to move on to the next camera, and this data, it's going to try to see if it can infer that are involved in that match. And oftentimes, what happens is sometimes it'll say, yet infer the position of that camera. Once it goes through, it makes another pass and says, okay, was the ability, basically I got all these cameras. So with all the information that I have, can I? Sometimes it does, sometimes it doesn't. Okay. Which it'll tell us which to report. In other words, it calls these things cameras, although it's all of those dots a camera, and it'll show us which cameras were not calibrated. In other words, position of the camera at that particular. And it obviously helps that we have a GPS location for that, but it still doesn't know. There's things that we can do to do that later. Like we can, okay, well, you didn't see this key point, but we know it exists. We can talk about that. It's still processes to run through here. Key points. When it gets through to the end, it'll go to 2 because it'll found all the matches. And then that'll work all the way through so it's got a report. That's one of the steps. That takes like a half a second. I mean the preliminary orthophotograph. So this process in about 15 minutes. So and we'll finish this up. I'm not actually gonna. I'll start it, but I'll take like another couple hours to actually do the steps. So that's something that you could do if you wanted to do it on your own. Just once during the course of the semester, not necessarily. All right. Yeah. Recording and get too big.